Okay, this is question 2. It reads, the figure below shows a wheelbarrow and stones with a total mass of 43 kilograms. The wheelbarrow is in equilibrium with two of the three forces acting on it shown in the figure. The first question is, identify the nature and point of action of the third force acting on the wheelbarrow. Okay, so let's take a look at the wheelbarrow. We see we have the weight acting downwards at this point. That's one force. We see the applied force acting upwards at the handles, and we can come up with the third force as the reaction that occurs where the wheel touches the floor. So we can put a reaction force right here. Can label it R. So the reaction acts where the wheel touches the ground. The next question says to write down an equation showing the relationship between the three forces. Now we want an equation that includes all three forces. So taking what we know about equilibrium, when a body is in equilibrium, one of the things we know is that the sum of the forces in one direction is equal to the sum of the forces in the opposite direction. So that would allow us to include all of the forces. So the forces the force acting down, there's only one force. So the weight is equal to the reaction plus the applied force. So this is our equation that shows the relationship between all the three forces. Okay, continuing on, part 3A says calculate the weight W. So we know the equation to calculate the weight as W equal M times G. And they gave us previously that the mass is 43 kilograms. So that mass here is 43 kilograms, and G, we will use G as 10 newtons per kilogram. So therefore the weight is 43 times 10. That's 430 newtons. So that's the weight, and this is part A. Now on to part B. Part B says calculate the value of the applied force. So we want to calculate what is F. Now let's just bear in mind that there are two equations that we can use. The first equation we wrote previously, it came from the principle of equilibrium, that the sum of the forces in one direction is equal to the sum of the forces in the opposite direction. But I'm talking about it because I want to point out that we cannot use it in this instance. That's because we do not know at this point, we do not know what R is. So we cannot use this equation in this instance. We have to use the principle of moments that says that the sum of the clockwise moments about a point is equal to the sum of the anti-clockwise moments about the same point. So let's choose that point as R. Now, interestingly enough, if we make this point the fulcrum or the turning point, we eliminate the moment due to R, simply because the moment due to R would have been R times the distance between the line along which R acts and the actual turning point, and that distance literally is 0. So the moment due to R is 0. So in taking moments about R, we literally eliminate the moment due to R. And then we are left with moment due to the weight and moments due to the applied force. Okay, so let's put those in an equation and let's see what we get. So the weight provides clockwise moments about the turning point. So that will be weight times the distance. So the distance would be the distance between the perpendicular distance between the line of action of the weight and the turning point. So that's this distance we're interested in here. So that's W times 0.6 meters. So that's equal to this, and this applied force F is providing anti-clockwise moments. So we can calculate that by multiplying F times the distance, the perpendicular distance between F and the turning point. So this would be F times 1.5 meters. So that's this distance we're interested in here. So looking at this equation, we can go ahead and solve for F because we know what W is. So let's substitute W. W is the weight. So the weight is 430 newtons. So that's 430 times 0.6 is equal to F times 1.5. Alright, so 430 times 0.6 is 258. So that's 258 is equal to F times 1.5. So now we're trying to find out what F is. If we divide the right hand side by 1.5, F will be standing on its own. And then if we do that, we also need to divide the 256 by 1.5. So that's what we will do. We say 256 divided by 1.5 is equal to F. Okay, so that's 256. Ouch, it's 258, sorry. So that's 258. It's 258. Divided by 1.5. Okay, so F is equal to 172 newtons. So that's the value of the applied force. Okay, if we wanted to practice a little bit, writing this to the most appropriate number of significant figures, looking back at the numbers that we worked with. This number 430 has two significant figures. This one has one significant figure. This one has two. So ideally, our answer should be written to one significant figure. So to round this up to a number that contains only one significant figure, that will give us 200 newtons. And this is correct to one significant figure. Okay, but this will pass as your answer for now. Okay, so that's it for this question.